As mentioned in the video about face portraits, the first thing we should do when constructing a face portrait is to find the invariant sets of the system. For second-order time-invariant systems, these invariant sets are equilibrium points, and possibly also periodic solutions, like limit cycles. When we have found the equilibrium points, the second step should be to determine which type of equilibrium points each of these are. This is called doing a local analysis. What we do then is to determine the qualitative behavior of the system near the equilibrium point by first linearizing the system about the equilibrium point, and secondly, finding the eigenvalues of the resulting system matrix A, and finally, classifying the equilibrium point. We will go through this step by step. How to find equilibrium points was covered in a previous lecture. Briefly stated, what you do is that you first write the system in state space form, and then you set the right-hand side of the differential equation to 0 and solve for x. The solutions are the equilibrium points. For those equilibrium points that are isolated, meaning that none of the neighboring points are equilibrium points, we do a local analysis. If the equilibrium point is part of a whole line of equilibrium points, for instance, then it is not an isolated one. The first step of doing a local analysis to determine the qualitative behavior of the system close to this equilibrium point is to linearize the system about the equilibrium point. I'm sure that you have learned how to linearize a scalar system, but in case you have not learned how to do this for a multivariable system, we will go through this here. Given a two-dimensional time-invariant system, and say that we have found an isolated equilibrium point x1 star and x2 star. From calculus, we have Taylor's formula, which gives that under the condition that the functions f1 and f2 are continuously differentiable, the function fi, where I can be 1 and 2, equals the function evaluated in the equilibrium point, x1 star and x2 star, plus the first order derivative of f with respect to x1, evaluated in the equilibrium point and multiplied with delta x1, where delta x1 is the difference between x1 and the value that it has in the equilibrium point, x1 star, plus the first order derivative with respect to x2, evaluated again in the equilibrium point, times delta x2, and delta x2 is the difference between x2 and the value that x2 has in the equilibrium point, x2 star, plus higher order terms of delta x1 and delta x2. So terms involving delta x1 squared, delta x2 squared, delta x1 cube and delta x2 cube, and so on. That x star is an equilibrium point means that this term here equals 0. And when we are close to the equilibrium point, so that delta x here is small, then these higher order terms in delta x1 and delta x2 will be very small compared to the first order terms, delta x1 and delta x2. So we can drop these terms, saying that they are approximately 0. And we can thus approximate the nonlinear state equations, the original ones, with this linear system. But note that this is an approximation that is only valid as long as the assumption that the higher order terms are approximately 0 is a valid assumption. So the linear system is only a valid description of the original nonlinear system when the states are sufficiently close to the equilibrium point. Note that the system matrix A is the Jacobian of the vector function f. The second step in doing a local analysis is to find the eigenvalues of the system matrix A. This you know well from previous courses on linear systems. You simply solve this equation here for lambda. And since it's a second order system, you will find two eigenvalues. The third step is to classify the equilibrium point, determining which type of equilibrium point this is. We will not go into the details of solving linear differential equations, as that is assumed known. If you want, you can refresh your memory about solving linear ordinary differential equations by reading section 2.1 in Khalil. If the eigenvalues are real, then we have three possible scenarios. Either both eigenvalues are negative, both are positive, or one is positive and one is negative. In the first case, when both the eigenvalues are negative, the equilibrium point is a stable node. The phase portrait of a stable node looks like this. Remember that the phase portrait gives us information about the qualitative behavior of the system. From this phase portrait, we can see that all the trajectories converge to zero without any oscillations. This is an overdamped second-order linear system with a time evolution looking something like this. From some initial state x of 0, the state will converge to 0 without any oscillations. The phase portrait that I sketched here gives a normalized picture of the system behavior, describing the particular case when A, the system matrix, is a diagonal matrix with the eigenvalues along the diagonal, such that x1 and x2 are the eigenvectors corresponding to lambda 1 and lambda 2. So this is how the phase portrait will look like if you write the system in modal coordinates, that is, if the eigenvectors are along the coordinate axis. If they are not, then the phase portrait gets a little distorted, like we see here. Here, the eigenvectors are no longer along the x1 and the x2 axes, but instead we have one eigenvector v1 here and another one v2 here. v1 is the eigenvector corresponding to the slow eigenvalue to lambda 1, and v2 is the eigenvector corresponding to the fast eigenvalue lambda 2. Up here we see that when the trajectory comes close to the origin, it becomes parallel to the x1 axis, while here it becomes parallel to the v1 axis as it approaches the origin. And in the normalized phase portrait, when the trajectory is far away from the origin, it becomes parallel to the x2 axis, while here it becomes parallel to the v2 axis. So for a general system, the normalized portrait here gets a little distorted, but the qualitative behavior is the same. The trajectories all converge to 0 without oscillations. In the case where both the eigenvalues are positive, the equilibrium point is an unstable node. The phase portrait of an unstable node looks like this. It is similar to that of a stable node, with the exception that all trajectories now move away from the equilibrium point. Specifically, all trajectories go to infinity without any oscillation, so the time evolution will look something like this. Starting from some initial state x of 0, it goes to infinity without any oscillations. This phase portrait here gives the normalized picture of the system behavior, describing again the particular case when A is diagonal with the two eigenvectors lambda 1 and lambda 2 along the diagonal, which is what you get if you write the system in modal coordinates. Transforming the system back into the x-coordinates, the phase portrait again gets a little distorted, like this. Finally, if one eigenvalue is positive and the other one is negative, then the equilibrium point is said to be a saddle point. And the normalized phase portrait looks like this. Note that along the x1 axis, which corresponds to the unstable eigenvalue lambda 1, the trajectories move away from the equilibrium point. And along the x2 axis, which corresponds to the stable eigenvalue lambda 2, the trajectories move towards the equilibrium point. And the other trajectories have hyperbolic shapes, none of them moving towards the equilibrium point. So the only trajectory that moves towards the equilibrium point is along the x2 axis. You may think about the pendulum example and the equilibrium point where the pendulum is standing straight up. This equilibrium point is a saddle point. Depending on the initial state value, the pendulum may have exactly sufficient initial velocity to reach the upwards equilibrium point. And for all other initial states, the system moves away from this equilibrium point. And this is how the phase portrait of a saddle point may look like when the system is not written in modal coordinates. We also have the special cases when lambda 1 and lambda 2 have the same non-zero value. Then the system is critically damped, or we may have it the case when lambda 1 and or lambda 2 are 0. You can read about these special cases at page 41 to 46 in the book by Khalil. If the eigenvalues are complex in this form here, then we have three qualitatively different cases. If alpha is 0, then the equilibrium point is called a center. And in the normalized case, where the system matrix A is in this form here, alpha minus beta, beta, and alpha, then the trajectories look like this. That is, the trajectories are circles around the equilibrium point. If it is not the system eigenvectors along the coordinate axis, then the trajectories will be a little distorted compared to this normalized picture here, and may for instance look like this. But the essence of the behavior will be the same. It is a marginally stable system, also called an undamped system, where the system states will oscillate with a constant amplitude and a constant frequency around the equilibrium point. The frequency of the oscillation will be given by the system parameters only, while the amplitude will be given by the initial state. If the initial value is here, then the system will follow this trajectory, moving around the equilibrium point, oscillating with the amplitude given by this initial state. While if the system starts in this initial state, it will follow this trajectory instead, oscillating around the equilibrium point with another amplitude. If the real part of the eigenvalue is negative, then the equilibrium point is a stable focus. The trajectory then spirals in towards the equilibrium point. This means that the system states converge to zero with oscillations, as the trajectory spiral towards the origin. In linear systems analysis, you may have called this an underdamped system. In the last case, the real part of the eigenvalue is positive, and then the equilibrium point is an unstable focus. Also in this case, the trajectory is a spiral path, but it spirals away from the equilibrium point. This means that the system states oscillate with larger and larger amplitude towards infinity. So to sum up, we have linearized the system around the equilibrium point of interest, and looking at the eigenvalues, we can classify the equilibrium point as a center, a stable or unstable focus, a stable or unstable node, or a saddle point. Why is this interesting? It is of course because we hope that the behavior of the original nonlinear system resembles the behavior of the linear approximation, but can we be sure that it will? Consider a general nonlinear second-order time-invariant system, which we have seen can be written in this form here. And assume that f1 and f2 are continuously differentiable functions. The reason for this assumption is that if they are continuously differentiable, then this implies that they are analytic functions, which means that their Taylor series representations converge. And this is important since the linearization we did was based on this Taylor series representation. So what can we say about the behavior of this nonlinear second-order system from the behavior of the linearized system? It can be shown that as long as the real part of both eigenvalues is non-zero, then the local phase portrait is topologically equivalent with the phase portrait of the linearized system. In other words, in a small neighborhood of the equilibrium point, we can approximate the behavior of the nonlinear system by the behavior of its linearization about this equilibrium point. So, close to the equilibrium point, the phase portrait of the nonlinear system will resemble the phase portrait of the linearized system. So, if for instance the equilibrium point of the linearized system is a stable focus, then the phase portrait of the nonlinear system will resemble the phase portrait of a stable focus near the equilibrium point. I will repeat it again just to make sure that you make a note of this. This is a local result. The resemblance is only guaranteed near the equilibrium point, and that is because the local analysis is based on a linearization, where we disregard all the higher order terms of the error coordinates. And this is a valid approximation as long as the error coordinates are sufficiently small, meaning that the system is sufficiently close to the equilibrium point. And the resemblance is only guaranteed if the real part of both eigenvalues are non-zero. If instead the equilibrium point of the linearized system is a center, meaning that the eigenvalues have zero real part, then we cannot conclude anything about the behavior of the original nonlinear system based on the linearized one. The behavior around the equilibrium point may resemble a center, but it may also resemble a node or a focus or a saddle point. We just don't know based on the linearization. So to sum up, how do we do a phase plane analysis? The first thing we do is that we find the equilibrium points of the system. Then we perform a local analysis about each of the isolated equilibrium points, meaning that we linearize the system about the equilibrium point. We find the eigenvalues of the resulting system matrix A, and we classify the equilibrium points. And then, unless the real part of an eigenvalue is zero, we know how the system will behave locally around each equilibrium point, and this will guide us in the next step, which is constructing a phase portrait using either the analytical method or using computer simulations. There is just one more thing that we should do as part of a phase plane analysis, and that is to see if the system has more invariant sets than the equilibrium points that we have found already. I have written this as the last bullet point, but actually this is something that you may want to do before constructing the phase portrait, such that you can use also this information to guide you, helping you to find the regions of interest in the phase plane.